Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. This video will explore Fortran and the program for matrix multiplication. In the previous video, we worked with a Python program to set up an interactive job on the compute nodes. This program is essentially a text file that is transformed into an executable program when executed. However, the process differs for Fortran programs. Unlike Python, direct execution of a Fortran program isn't possible. Instead, a Fortran compiler is required to convert the Fortran program into an executable file before it can be executed. A prominent compiler in this context is the iFort Intel Fortran compiler. Fortran, the longest-standing programming language still in widespread use, was born in 1957, with its initial standard released in 1966. Undergoing continuous updates since then, Fortran remains a pivotal language in high-performance computing. Its evolution spans standards like Fortran 66, 77, 90, 95, 2003, and 2008, and Fortran 2018, and the most recent, Fortran 2023, released on November 17th last year. While widespread adoption of fully compliant Fortran 2023 compilers is pending, recent updates to the Intel Fortran compiler have incorporated some minor additions. Of particular interest in Fortran 2023 are new functions like split and tokenize, tailored for efficient extraction of tokens from strings. The iFort compiler, short for the Intel Fortran compiler, is developed and distributed by the Intel Corporation. It forms part of a comprehensive set of compilers, libraries, and tools tailored for high-performance computing, artificial intelligence, and data analytics. Specifically, the iFort compiler focuses on transforming Fortran source code into executable binaries. Recognized for its advanced optimization features, the iFort compiler can automatically apply techniques like loop unrolling, inlining, and vectorization to enhance the compiled code's performance. The compiler's automatic vectorization capability utilizes single instruction, multiple data (SIMD) for parallelizing operations on multiple data elements. Let's revisit the Fortran program for matrix multiplication. In Fortran, the program typically begins with variable declarations, a practice not required in languages like Python. While unnecessary in some languages, many find this beneficial as it offers a clear overview of the variables used in the program. Begin your declarations in Fortran with the instruction implicit none. In the absence of an implicit none declaration, the compiler defaults to interpreting variable names starting with letters A through H as real values. And those starting with O to Z are also real. For names starting from I to N, the compiler assumes they are integers. Without implicit none, even a variable named God would be assumed real. Therefore, it's crucial to apply implicit none to avoid unintentional assumptions and to ensure that God is not assumed to be real. I'm using the declaration instruction integer, kind equal to 4, indicating a 32-bit integer. In this context, the maximum value for a 32-bit integer is 2 raised to the power of 31 minus 1, which equals 2,147,000,000 483,647. In the program, the variables I, j, k, and write c and n are all integers. I utilize the parameter option, making the variable n a constant set to 2048. This implies that n's value remains constant throughout the program's execution, and it is known at compile time. I'm employing the declaration instruction real, kind equal to 8, indicating a 64-bit real. In the program, the A and B and C and TMP variables are of real type. The choice of associating kind equal to 4 with 32-bit and kind equal to 8 with 64-bit architectures is primarily a historical convention and a standardization practice in the computing field. However, it's important to understand that kind equal to 4 and kind equal to 8 may not always correspond to 32-bit and 64-bit data types, although this is typically the case with most Fortran compilers. The declaration using these kinds may not be as intuitive for humans. We'll explore a more user-friendly approach in our upcoming videos. A real 64-bit number can be expressed as a significant times 10 raised to the power of the exponent. The sign, whether plus or minus, takes up 1 bit, the exponent occupies 11 bits, and the significant uses 52 bits. The maximum exponent is 2 raised to the power of 10 minus 1, equal to 1023. To estimate the number of decimal places for the significant, we can use the 10 base logarithm of 2 raised to the power of 52 minus 1, approximately yielding 16. I employ the dimension option, declaring the A and B and C variables as 2-dimensional arrays or matrices. I have also declared a character or text variable with 20 as the maximum numbers of letters or characters. In the first do loop, I initialize matrices A and B with values through a double-nested loop over I and j. To convert the integer values of I plus j and I minus j, I utilize the intrinsic function real. Moving further down the Fortran program, we encounter the do loop responsible for matrix multiplication. You can explore the details of matrix multiplication on Wikipedia. Matrix multiplication, first introduced by mathematician Jacques Binet in 1812, stands as a fundamental tool in linear algebra. Its applications span across various fields, including mathematics, applied math, statistics, physics, economics, and engineering. This operation holds a central role in computational applications of linear algebra, and we'll be utilizing the index formula for matrix multiplication. Now, revisiting our Fortran program, the loop employs the index formula and executes a well-known method known as an accumulative sum. This method, fundamental in numerical computing, involves accumulating or summing up values over a loop or a series of iterations. The computation within the accumulative sum looks like TMP equal to TMP plus something. Here, the variable TMP serves as the accumulative variable and needs to be set to 0 before initiating the summation. It's crucial to note that this loop is triple-nested over I, j, and k. This loop encompasses the majority of the computation and holds paramount importance in parallel computing for this program. The remaining portion of the program is enclosed within a Fortran if statement, executing only if the variable write c equals 1. This section is responsible for writing the elements of the C matrix to a file, allowing us to verify that various parallel computing methods produce consistent results with the non-parallel execution of the Fortran program serving as the reference. It's worth noting that we've set the right C variable to 0, indicating that we won't execute this program segment during performance testing with different Fortran compilers and compiler options. To conduct Fortran compiler testing on the program, I've crafted a Python script situated in the same directory. You can see the script, named testing, in the Emacs editor. In this Python program, I've imported the OS and time modules. As discussed earlier, the OS module enables the execution of Linux commands from the Python script. The time module is employed to measure the wall time during the matrix multiplication performed by the Fortran program. The variable file name holds the name of the Fortran program, while exename stores the name of the executable program generated by the Fortran compiler. The variable compiler stores the name of the Fortran compiler, specifically the iFortIntel Fortran compiler in this instance. Meanwhile, the numerical variable numxe represents the number of times the program will be executed. This allows us to calculate the mean wall time for the matrix multiplication performed by the Fortran program. If the compiler is iFort, the program will utilize the compilation options outlined below. The compile option vector comprises 3 text strings, the first being O3, the inclusion of the march option as the second, and finally, the replacement of O3 with O_fast. These options will be discussed in our forthcoming video. As we scroll down the Python script, we encounter the Python loop. This for loop is nested, iterating over the variables, option, and I. The I loop operates similarly to Fortran's do loops, incrementing I from 0 to 2. This range stems from the variable numxe being set to 3, aligning with Python's zero-based indexing. However, the option loop diverges from the Fortran do loop because option is a text variable. It contains the text strings from the compile option vector, representing various compilation options we'll explore. The doCompile text variable denotes the compilation command structure. It comprises the compiler variable, designated as iFort here, and followed by compiler options and the Fortran program's file name. Additionally, it includes the -o string followed by the executable program's name, indicating the desired name for the compiled executable. The following 2 lines initially display the complete compilation command in my terminal and then proceed to execute it. The execution command will be // followed by the name of the executable program, and the OS system will handle this. The I loop will iterate 3 times. The start and the end variables utilize the time module, where the wall time represents the difference between the end and the start. Subsequently, the wall time is printed to the terminal. We utilize the accumulative sum method to determine the total wall time, enabling us to compute the mean wall time. This average wall time is then printed to the terminal. We're now prepared to conduct interactive testing of matrix multiplication using the Fortran program, which we'll explore in our upcoming video. If you're interested in learning more about Fortran, consider watching the Introduction to Fortran videos on this YouTube channel. These videos explore a range of topics in depth. While I will cover some aspects, my primary focus is on parallel computing. The Introduction to Fortran videos provide detailed explanations and practical examples to enhance your understanding. I am looking forward to the next video, wishing you all happy computing in the meantime.